Okay. Okay, so for the first 15 minutes presentation, so we have Vincent Eberle, spatially varying variant point space functions for Bayesian imaging. So please.
Welcome back.
No, it's not. Oh, no, it's, you switched off the microphone. Yes.
Check.
Yeah, it's good.
Great. So welcome back from the coffee break, and welcome also to the last session of this wonderful conference. My name is Vincent Eberle, and I'm a PhD student at the Max Planck Institute for Astrophysics in Munich, and I want to talk about spatially variant point spread functions for Bayesian imaging. So to start, I want to have a short look at this image. It's the first light image from Rosetta X-ray telescope. And what we clearly can see is that here the effects of the point spread functions still distort the X-ray observations to some degree. When I'm talking about point spread functions, you can kind of categorize them into two categories: spatially invariant point spread functions and spatially variant ones. So here we clearly have spatially variant ones because they change the off-axis angle with the azimuth and with the energy, which can also be seen in this graph, which was done, mapped out at the laboratory in Garching. So not only Rosetta has this problem, but also Chandra, which is another X-ray mission. So here we can see the same behavior from left. On the left side, 1.5 keV approximately, and we see that the point spread function changes over the, is this working? Yeah, over the azimuth and over the off-axis angle. And also we see that for different energy bands, that there is a different point spread function as well. So actually this affects not only X-ray emissions, but also microscopy and medical imaging and many other devices. So when will we have instruments without this effect? Never, probably, because aberration will always affect these things, but actually I don't care, I just don't want to wait, so we try to fix this differently. So why is it non-trivial to remove these effects? Basically, there are 2 points. One is deblurring noisy images is just a challenging task, and the other one is representing an inhomogeneous point spread function is also not that easy in the first place. So the first one we can kind of tackle with information field theory and generative modeling. Let's have a look at this. What is information field theory? Basically, it's information theory for fields, making heavy use of Bayes' theorem, which connects the posterior with the likelihood and the prior. So as soon as we have this posterior, we can calculate the posterior mean for some quantity or the posterior standard deviation, or just have a look at the posterior samples. For that, we need some knowledge about our signal, which can be encoded in our prior. And also what we need is a likelihood term. In this case, since we have photon count instruments, it's a Poissonian likelihood, which connects the count rate, the average count rate, with the number of counts we collected. And this average count rate can just be represented as our sky flux fed forward through some instrument response. All of this is just theory, but if you want to implement it on your computer, you can make use of Nifty, which is a Python package, which can be used for generative models, for Bayesian inference, and using information field theory, which comes with its own inference algorithm, which is called geometric variational inference, and you can read about it in Frank et al. 2021, or if you manage to see a talk from Philip Frank, I can highly recommend. So generative models, in total we saw them like pretty often this week, but this is like a computational graph for one, and what we feed in is Gaussian white noise, and then with some handcrafted operations we can, for example, get some correlated structures or non-correlated structures, which could be some dust or some point sources. The combination of these two sources could be like a model for our prior sky. So in total, this part of the graph can be the encoding of our prior. So as soon as we have like a model for our instrument, which is here, one of the instruments is R1, we can basically, together with the data and our likelihood, encode our likelihood. So this we kind of wrapped up. So the deblurring of the noisy image shouldn't be a problem as soon as we take all the statistics and everything into consideration. So still, we have the problem of the PSF representation. PSF representation, why is it a problem? So there are, as I said before, these two categories of PSFs, the invariant ones and the variant ones. For the invariant ones, we don't have a problem because they're just a convolution with one PSF kernel, and basically it's a fast Fourier transform. So you go to Fourier space, you multiply, you go back. And basically, this is on the complexity order of n log n, which is fine. But spatially variant ones are not a convolution. So the naive approach could be to use a full matrix representation, but this scales with n squared, and as soon as you have an image with 1,000 by 1,000 pixels, this would be 10 to the 12 matrix entries. So this is kind of alone the memory would consume 8 terabytes. So this is not feasible. And also it's super slow for execution. It would scale to n to the 3. So the conservative ways to deal with spatially variant point spread functions would be to either deconvolve with an average PSF or remove all the off-axis data and so kind of get rid of the problem this way. But the problem is by removing the off-axis data, we just decrease the signal-to-noise ratio at the end. So I was searching for ways how to represent these spatially variant point spread functions differently and found a method from a pretty old paper, which is called patched interpolated convolution. And basically, it's pretty easy. So you take your image in the forward pass, divide it up in some patches, and then the only information you really need is you need the PSF for the center of each of the patches. For most instruments like Chandra or some microscopes, you either get this from your simulation of the instrument or you can get this from some measurements in the lab. Then you cut out with some overlap, which is then basically you cut up onto the center of the next patch, and this you do for all your patches. This cutout you multiply with a bilinear interpolation kernel, so you have, in order to make sure that you don't copy too much flux into each of the patches, so that by adding up at the end, you don't have too much flux anywhere. And this interpolated cutouts, this weighted cutouts, you then convolve with your kernel, so you have like every patch is convolved with the local PSF. So these cutouts you then just add up together, which results in an interpolated, bilinear interpolated image where the point spread function is changing linearly into each direction. Doing this with 4 patches wouldn't solve the problem, but as soon as you have like multiple, large number of patches, this kind of approaches the real PSF. And still the computational complexity is on the order of n log n with some multiplication factor, which is, let's say, m, and this is the number of patches you have. So we have a kind of sparse representation of this PSF. Combining these two methods, like information field theory and patched interpolated convolution, we can come up with a Bayesian denoising decomposition and deconvolution algorithm, which is also suitable for spatial variant PSFs. So enough talk. We can now apply this to Chandra. And for this, I basically took the Chandra marks tool where you can simulate your PSFs for different off-axis angles and fed these information for our patches. So to look at the synthetic or mock forward pass, so this could be our mock sky observed for 3 different off-axis angles of Chandra, where you can clearly see that this really changes how Chandra sees this sky. And the yellow stars just mark where the optical axis should be. So then we tried to apply this to real data. We wanted to image pair-size cluster. Therefore, we basically binned the data into 3 energy bins, namely these ones, and wrote a generative model for a diffuse and a point source component. And then we assumed spatial and spectral correlations. So far, so good. So this is the exposure-corrected data, which is, you see, pretty noisy. You have huge PSF in the middle. And if you take all this information and the generative modeling into consideration, you can basically come up with a posterior mean integrated sky brightness, which looks like this. So you see that we can get rid of a lot of noise and already deconvolve to some degree. And this we can do for all 3 energy bins. So, but you never have like this stage that you only have this one observation. That's the thing why we originally wanted to do it, so that we can kind of also merge different observations without increasing the smearing out from one observation to the next one. So if you combine the different likelihoods, we can come up with like a much sharper image. And we had this discussion on Tuesday about interpretability of latent spaces. So if you, as soon as you do the generative model in a handcrafted way, you can basically decompose your sky again into a correlated diffuse part and to point source-like stuff. So that's a kind of an advantage. So I did another short example on Cassiopeia A, where I took this observation. And what you can see here, I don't know if you see it in the beamer, that this part is differently smeared out than, for example, this part. So this is really heavily affected on these different parts with different PSFs. And doing, in this case, only a map regression, we came up with this much sharper image. We can zoom in, we compare it first like this. So you can also see left to right that it's got, so the left one is the data and the right one is the inference. And you see here that at the encircled parts, it's got much sharper. Zooming in, we can have additional looks on this. So left is the data and right is the sharpened one. And here as well. So to come back to my first slide, to the first image of Erosita, we basically did this as well for this image and wrote all this PSF deconvolution algorithm as well, also for, not only for Chandra, but also for Erosita, together with my two colleagues, Matteo Guardiani and Margaret Westerkamp, who are also on this conference, and basically came up with this solution. So basically there's still some room to make this even better, but I think we already did some good job to deconvolve this. Yeah. So to summarize, removal of spatially variant point spread functions is possible despite Poisson noise, and it enables us to also incorporate far off axis observations and stabilize point source detection. For the future, we basically want to make this even we want to find faster and even more precise representations of the point spread function, and perhaps we would also like to infer PSF or other detector effects from redundancy in data. So if you want to know more about the IFT, NIFTY, or PSF representations, just let me know. Thank you, and I'm open for questions.
Thank you. We can maybe have one quick question here and New York. So here, I see Nabila.
Thank you, great job. Did you try it for other type of images and like deblending or other type of sources, or I mean, is it just applicable for the X-ray and X-ray?
At the moment, we just did it for X-ray.
Okay, but I guess you plan to extend it.
Yeah.
Okay.
New York, any question?
Any question here? Yes. Yeah, hi, thanks. So for the example images you showed, what's the typical resolution of the image and how many patches you chose?
So the resolution of the images is about half arc second, and or you mean like the number of pixels?
I guess both.
So it's 1 pixel is about half an arc second, and it's for the Cassiopeia A thing, it's 1,500 by 1,500, and for Perseus it's just 500 by 500. And there the spatial resolution is a bit higher. The number of patches is great. Sorry?
Sorry, go ahead.
So the number of patches is actually 8 per side, so it's in total it's just 64 at the moment. But one could possibly also increase it more.
Thanks.
Okay, we thank the speaker again.